Okay.
Okay, last time when we were discussing it, we were finishing up with discussing the Laplace transform. We just started discussing the idea of the Laplace transform, gave you the basic integral transformation that it uses. I thought we'd spend the next few minutes discussing some example problems that can be solved using the Laplace transform and show you how it's done. I'm not an expert in Laplace transforms, but I just know enough to do some of the problems we've got in the book, like in electrochemistry sort of things. And so if you want to know more, you'll have to probably read in the book some more and maybe pick up a book on Laplace transforms. So what we're talking about today should be sufficient to get you through a lot of the problems in the book that use Laplace transform for solutions. All right, well, as we were finishing, let me see if I can get to my spot here. We were doing some examples, and one example of the Laplace transform, I think we made a little table. We said, what's the if the function of time is equal to e to the minus kt, a common sort of expression, particularly for electrokinetics. What's the f of s value? Well, as we remember, the integral transformation is from 0 to infinity of the f of t, which is e to the minus kt, times the Laplace transform process, e to the minus st, and take that derivative with respect to time. So only the time derivatives on this Laplace transform are being used using the Laplace transform. And that can be easily rearranged, I think, as we mentioned last time, to give us this form of the problem. And that the solution to that integral equation is like so. And we evaluate again from 0 to infinity, and that would be 0 minus 1 over minus s plus k. So the table, I think, was we can make a little table of simple ones, f of t, f of s. We said a constant would be in the Laplace space a over s, the constant over s. E to the minus kt would be 1 over s plus k in Laplace space, and t would simply be 1 over s squared. And I think you can all verify those relationships doing the integral transformation directly yourself. A lot of the Laplace transforms have already been worked out for you, and so you can look up tables of Laplace transforms. And I've also mentioned that a lot of programs now, such as MathCAD and Maple and Mathematica, will let you do symbolically do these Laplace transforms. So you can just plug in the equation and it'll give you the Laplace transform. Let's go to something a little bit more difficult. Let's ask ourselves, what's the Laplace transform? And I'll use LPT as a shorthand for that, LPT, Laplace transform for this. So what's the Laplace transform of a derivative? So in other words, given a function of time, which is dy dt. Well, we apply, just like before, the integral transformation. So we have the Laplace transform of dy dt is equal to the function in the Laplace space, and that, of course, would just be the integral transformation of e to the minus st, their Laplace transformation, and dy dt dt. So here's our integral transform. Here's our function of time. And that's the way we do it. Now, this sort of a problem in calculus is a problem you'd have to usually solve by doing integration by parts. And so let me just go through that simple thing. It's probably been a long time since you had calculus. It's been a long time for me. So what we can do is we can integrate by parts by taking these two parts of the integral, let's call this part u, let's call this part v, and we can integrate by parts there. Remember that the derivative of a function that's a product, say derivative of u times v, is equal to u dv plus v du. And so we can use that definition or that relationship in our integral by integrating by parts. And so integrate by parts, the formula is that the integral of u dv is equal to uv minus v du. And so our u part is is equal to e to the minus st, and our dv part is just dy, because we've already got this is v, so the dv part of that would just be dy. Well, du, we can quickly do the integral of that. Remember, the formula for integral of an exponential is just what's in the exponential part, so it'd be minus s e to the minus st, and v is equal to y. All right. So let's put that up here. And so basically we've got the problem solved. We've got the integration by parts. Integration of u dv is equal to uv minus the integral of v du. So we can plug that in. The first part, uv, would be y e to the minus st. And we, of course, would integrate or would evaluate them from 0 to infinity. The second part would remain an integral at this point. It would be 0 to infinity y to the minus s e to the minus st dt. And of course, that part would be the v du part. So there's v du part. And so continuing this, it's not dy, I'm sorry, I don't want the dt up there. Okay. And that's basically at the end of it. Now, in shorthand, we would write this in a little bit different way. And so the result for the Laplace of an integral would be 0, which is the evaluating that part, minus y to the 0, and plus s y bar over s. Okay, and so this is the function y at t equals 0, and this would be the Laplace function of s. Okay, so rewriting that, the Laplace transform of dy dt as a function of t would be, as you remember in calculus, you often use shorthand, use a little prime to indicate that dy dt process. And that would be s y bar s minus y0. Okay, so that would work for every situation for a derivative. And so we just plug in y there to do the process. So just taking the Laplace transform, whatever the y function is, would give you the part here. Doing the the evaluation of that function of y as t at time equals 0 would give you that part there. And this process can be continued, and you probably want to verify this for yourself, for say second derivatives as functions of t. Of course, you use that double prime to indicate that second derivative process. I'm running out of room here. Let's write this here. Minus y prime 0. In other words, the Laplace of a second derivative would be s squared, the Laplace function, or the Laplace unit s, times the Laplace transform of that y function, minus s times the function evaluated at time equals 0, minus the first derivative of the function at time equals 0. And so for a triple derivative, or the third derivative, we get something like this, where we have s squared, the Laplace transform at s of y, minus s squared times the function at time equals 0, minus s times the second derivative evaluated at time equals 0, minus s times the first derivative evaluated at time equals 0. Okay. Got everything on there? Good. So derivatives, as a rule, are pretty straightforward. You just plug it in. You can either do the evaluation yourself after you do it, or you can use this formulas that I've shown you. So the only tricky part in all these would just be finding the Laplace transform of the original y function. Okay, which may not be trivial, but the form of it is right there for you. Now, the next step up in complexity for Laplace transforms is to do Laplace transforms of ordinary differential equations. So ODEs. For example, an ordinary differential equation arises when you have a kinetic type problem, say A going to B with some rate constant K. You can have initial conditions, say at t equals 0, A would be equal to the bulk concentration, or the concentration at time equals 0, and A at, say, time equals 0, or a different way of writing it would be A0 would be A star. Well, the solution to this ordinary differential equation for finding the rate of change of A with time is minus Ka, and to find the value of A at any particular time, we can solve that using the Laplace transform. So let's go ahead and do that. Let's go into the Laplace space. And we already know dA dt, how to solve that. Okay. So here we see we've taken this part here, and so it's s y bar s minus y0, so that's s a bar s minus a star, which is the function at time equals 0, is equal to a star according to our initial conditions. And that's going to equal to the Laplace transform of that part here, minus Ka, which would simply be minus k times the Laplace transform of A s. Now A has to be transformed as into the Laplace space because it's a function of time, and that's what we're interested in knowing, is concentration of A at any particular time. So A bar S is equal to the initial concentration. And what we really are interested in knowing is this part here equal to A star over S plus K, and then getting out of that is the inverse Laplace transform. And we know that this form of the function A star over S plus K is an exponential form, as we've already written in a little table. If you remember going back to the original state, this form in the Laplace space gives us this form in the time space. So we can write down directly that A as a function of time is equal to A star e to the minus kt. So you've learned probably other ways to do ordinary differential equations, but you can see you can solve them in the Laplace space quite straightforwardly. And so that's easy enough. So most of the problem you're having in the Laplace space so far has been simply just algebra, manipulating the units around. Let's see if we can see something that's a little bit more complicated. Let's take a second derivative. In this case, let's say d squared of concentration. So some concentration as a function of a variable y plus the value minus a squared times concentration as a function of x equals minus b. And let's suppose that we don't really have any initial conditions here. So going into the Laplace space gives us, as we've already understood, s squared c bar s. So this is a second derivative, so we use our formula for the second derivative, minus s a minus b. Now these should be big A. I'm sorry, sometimes I'm using small and big A's, but this A is this A and this B is this B. Well, actually the way I've written it in my notes, I guess I'm using the big A to stand for the value of A at x equals 0. That's confusing, I'm sorry. Plus this part here, which we can take in the Laplace transform directly. And the equal sign minus b would be equal to minus b over s. So what you're seeing here is that instead of a time function, we're using x as that time instead of time. So we can do that as long as we say, rather than time, we're just going to use a value with respect to x instead of time. Well, we can rearrange that to give us this particular form. And that would be a result. So this is the Laplace form of the concentration, say, with respect to x in the Laplace space, and that would be this particular form of the equation, the concentration of A at x equals 0, concentration of B at x equals 0, minus B over S is that. Redoing our algebra a little bit, we can see the following is true. multiplying by s, and we can extract the following form of that equation. Now to fraction this, we use partial fractions. And they're in the book, and you can see a description of partial fractions and how to use them in the book. I'm not going to really go through the whole thing. It's just a math trick, basically, so you can look through that yourself. But we find that this function c bar s can be made equal to a set of parameters d prime over s plus a prime over s plus a plus b prime over s minus a. Now, in order to get a factor here, which is the factor d prime out of the system separately, so in order to solve that, we can actually go ahead and do a thing where we multiply by s and then set s equal to 0. So d prime is equal to b over a squared for s is equal to 0. So in other words, so d prime is the value of this function when s is equal to 0. Okay, see this part here. Multiply by s. All of this part, this is equal to s. And if you set s equal to 0, these terms drop out. And the only thing that's left is b squared over a, or b over a squared. Okay. Now, taking this expression, now that we know the value for this Laplace transform at s equal to 0, we can get out of the Laplace space and write that c as a function of s is equal to d prime plus a prime e to the minus ax plus b prime e to the plus ax. So let's go ahead and look again. Remember, we're solving an expression, something like this one here, d squared y over t. What we've got now with this thing is this value here is s y bar s to solve the thing. Now, so what we really need to know to solve this finally is to find values for a prime and b prime. And those values are not going to be available to us until we put in some initial conditions. We need to know basically what the concentration is at x equal to 0 and what the concentration of the derivative is at x at 0 to get the values for a prime and b prime. All right. Now, using what we've learned, we can go ahead and try something that's really what we're after in these electrochemical systems, and that's to solve partial differential equations. And really often just interested in one particular one in the next chapter, and that's this one here, the partial derivative of, say, concentration of O at x and t dt equals the diffusion coefficient of O d squared c sub O, again at x and t, as a function of x and t, dx squared. Now we can put in some boundary or initial conditions at least. At t equals 0, concentration of O is equal to the concentration of O in the bulk. So in other words, any x, any solution concentration at any position x in solution would be equal to the bulk. So here we got a partial differential equation for a fixed second law. At x approaches infinity, another condition that we can put on our system, a boundary condition, was that concentration of O as for a limit of x approaching infinity is again equal to C sub O star, the bulk concentration of O. Well, the Laplace transform of these functions would be like so, where we use again the bar to indicate the Laplace version of that. As we approach infinity in S, then we can just simply write that that boundary condition of the Laplace space would be C sub O over S, the bulk concentration of O over S. So we can use that later on as one of our boundary conditions in solving the form of the equation. So let's take our partial differential equation, take the Laplace transform. Again, we're going to use time as a Laplace function in this particular form of this case. Well, we can just write down for already what the form of the Laplace would be of the first part of the equation. Oops. That would be a derivative with respect to time, and so since x is not a Laplace variable, it doesn't get transformed in the Laplace space, it just stays the same. And so it'd be S bar y minus the value of that function at time equals 0, which is the bulk concentration. We've already established that. And so the next part would be the second derivative with respect to x squared, and since that's not a Laplace variable, we don't have to do anything to it. So that would just be d0, d squared, C sub O bar, xs over dx squared. So this is the equation that we're going to need to manipulate. So let's rewrite that. Okay. Now what we can do is take the Laplace transform again of this particular equation. And to get what we need out of it. We just did this. We just did a solution just like this in the previous page. So we can just write down directly the solution to a problem in this particular form. And we see that that turns out to be C sub O bar xs is equal to CO star over S plus A prime S e to the plus B prime S e to the minus S over D0, and then we got to put an X in there somewhere, so sorry, the X is up there. off of the page a little bit. Now, how do we figure this out? Well, we just have to find out values for A prime and B prime to get our final result. Let's take a couple of attacks at it. First of all, we know that as x goes to infinity, the Laplace function CO bar x sub s has to be equal to CO star over s, and that was one of our initial conditions up here. We've already shown that. So if we put that in for large values of x, we see that in order for that to be true, for that to hold, we have to make sure that A prime is 0. When x e to the x is when x is infinity, e to the minus x is very small. So this makes this term very large in the system, and that would make, the only way to make that work out then is to have A prime be equal to 0 for large values of x's. So we can imply that. So we can rewrite, now knowing what A prime is 0, we can rewrite CO bar xs is equal to CO star over s. Okay, just to reiterate then, since x is large, that this term here is very small too. So this term goes to 0 because the exponential goes to 0. Doesn't matter what B prime is. This term here goes to 0 because A prime has to be 0 in order to make it equal to 0, because that's the initial condition. So B prime s e to the minus s over d0 x. So in order to find this value of B prime, we need to have some other boundary condition, and we don't have that yet. And that's what's going to wait until we actually do some real problems. So in order to get out of Laplace transform space, we need to find out what B prime is, and then we can un-Laplace transform it and find out our solution. So a third boundary condition will give us that B prime value. So these functions, as we'll see, are concentration functions that we can use to solve our diffusional problems. The other problem that we want to know about is the current in our system. So in addition to knowing the concentration solution when we're doing a system, we also usually want to know the current that's flowing at any particular time. So we can start that solution by using Fick's first law. And remember, this term I as a function of t over NFA is equal to the flux at the electrode surface as a function of time of O, and that's equal to minus d0 and this partial, or this derivative, c sub O a function of x and t dx for x equal to 0. In other words, solving this is a concentration gradient at a particular time at the electrode interface. So the sharper the gradient, the larger amount of current is going to be flowing, as we'd expect. So we can Laplace this, and we find that I bar S over NFA is equal to the Laplace transform minus d0, and this would be equal to d CO bar xs. Again, because the x is not a Laplace variable, You don't have to do anything fancy with that. It just passes into the Laplace space as a constant, essentially, and we get that result. So we can, given this is our value b prime from before, we can substitute that in. Again, the b prime s is weighting our third boundary condition to do the current that's flowing. So in order to do the reverse Laplace transform, we need to find the third boundary define the third boundary condition, find the value for b prime, which is important, and then do the inverse Laplace transform. Same case with to find the concentration as a function of x. All right. And as we'll see in just a minute, we can solve those problems once we know those third boundary conditions. There's two real major problems in this Laplace transform method. It really only works for linear systems. For example, the transform really isn't defined for things like this, where the time derivative of a, dA dt, is equal to minus k a squared. That's a problem that really doesn't have a Laplace transform. The second problem is that the inverse transform, I've sort of just said, okay, we just do the inverse transform. Well, that's often a serious problem in itself, trying to find the inverse Laplace transform. And there are methods to do it. There's a thing called convolution integral that can solve those for you. Probably the engineers in the group have done this a few times, but we won't really worry too much about that because most of the problems are kind of solved for us, and we just want to get you started, and you can do that yourself, I think, without too much worry. I'm not really interested in the formula in this class, whether or not you can solve lots of Laplace transforms and solve all kinds of partial differential equations. What I do want you to know how to do is be able to look at a problem and suggest a possible way to do the solution, and then use these tools to find that solution. And so this will at least get you started on the road to doing that for you. So this is one way of doing it. And